part of this lab is to introduce basic accelerometer usage. And so I want to talk a little bit in general about accelerometers and the sort of the sensing mechanism, and then the next video I'll discuss the specific accelerometer that we'll be using in this lab. As mentioned in a previous video, accelerometers are basic-sided mass spring damper systems. This little figure shows sort of a basic concept of an inertial or seismic sensor, if you like. You have a case, and then suspended within that case, right, is this inertial mass, and as this thing bounces up and down on the surface, it excites the motion of this mass, and you need some mechanism that's really picking up the relative motion between the case, if you like, and that mass. And that sensing mechanism is a lot of different ways or a lot of different methods are used to detect that motion between those two, right? And so I'll talk a little bit about those. Right, this is showing, sort of very generic spring, explicit, discrete elements of stiffness and damping. That could be a material, or it could be a lot of different ways that you could make this. It's not necessarily a little coil spring in a damper, right? Again, you can make, once you understand accelerometers, you can make motion sensors this way. This book, nice little book by Forrest Mims, who used to write these little mini notebooks for Radio Shack, which I don't think these are around anymore, but he had one little book on sensor projects where he showed, look, you can buy these little piezo electric buzzers, and what these things do is as you stress them, there's a charge distribution that changes, and you can sort of generate a voltage. So you could tap this thing and you can generate a voltage across that. You could basically have a light sensor, or he actually put one here at the tip of this beam between two bricks and set this at his house, and this thing starts, the motion is coming in through here, right, on the ground, and this thing starts shaking, and so this thing picks up those motions. So this is really not you don't know, is it sensing acceleration? Is it sensing velocity? It all depends really on how you make this. And so if you're designing a sensor, then you have to go a little bit deeper, model it, and configure not only this, how things are, how things are made, but also the signal conditioning you use in order to sort of optimize it for certain kinds of which variable you're going to measure, and also what the sensing mechanism is, makes a big difference as to what it is that you're really picking up. And as I'll talk about later, what range of frequencies are being detected. You might be mostly that you're being more sensitive to displacement of the input, or velocity of the input, or the acceleration. So sometimes they have different names depending on, you might have a velocimeter, or you might have something that's more of a displacement sensor. Okay. So you can buy these little low-cost components, and these are some from SparkFun, one of my favorite places to buy low-cost electronics. But you can find these little piezo vibration sensors, right? So they're really just to detect motion, and they're so cheap, it's really there just to say, hey, something's happening. If you wanted to measure exact accelerations, it would take a lot of calibration to do that, and these are not what these are made for. Note that there's a little mass element, and there's this little white piece here is the piezo element that's generating a charge. It's just like those little piezo buzzers that I just showed you a second ago. Again, these would require maybe some additional signal conditioning. But they're pretty good for detecting motion. You want to just detect when someone's walking by, they'll give you a signal, and you can do something with that. You get what you pay for, and so more expensive accelerometers or other kinds of motion sensors are going to cost you more. They're going to be calibrated, and they could be more costly, from $3 some up to you might be paying something like $600 or $1,000 for higher grade sensors that have a wider range of frequencies they can measure, more reliable, and also more resilient, if you like. Piezoelectric sensors just use a different kind of mechanism. I've highlighted, where this mechanism is relative to the seismic mass. If you want to, think of the seismic mass as these pieces here, and again, the motion is up and down on both of these. But note, this is a compression type sensor. This one's a shear sensor. The sensing element is holding up, like, so this guy is moving up and down here with the case, right? And then these little seismic masses are shearing that little piezo element, so it's causing a shear, if you like, and that's how it's being detected. Whereas this one, the piezo element is responding to compression of that element, and they're built in different ways. Okay, piezo elements, pretty good for higher frequencies. Not so good because of the signal conditioning and because of how they work. When you compress these, the charge distribution tends to kind of be hard to hold, and so you lose the low frequency response, and we'll talk about that later on with respect to force measurement as well. But really good for high frequency measurements, and higher grade too. Say if you're looking at the response of aircraft wings, or higher vibration of high frequency vibrations. Usually a lot of those sensors that you might use are piezo. Right, lower frequency sensors I'll talk a little bit more about in a second, because that's kind of what we're using in this lab. There's also piezo resistive, which you also see. Not such high frequency, but maybe mid-range, if you like. And here's one that we used to use. It's actually, piezo resistive is a resistive type sensor. It's actually also, it's made on a MEMS type structure, and you can imagine they've made a little beam here, and the hinges have piezo resistive elements or strain gauge type elements. So you're detecting basically the bending here, and you can detect that the fact that this little mass, this inertial mass now, is this little beam. As this is moving up and down, you can measure acceleration that way, right? So, and this is again a very small device, actually this particular one was one that we used to use, made by a company called Sensortech, which is now a Honeywell company, and I'm not sure, this has been some time since we bought this. Is quite some time ago, 97. But I like this one because when I bought these, they actually had a little certificate of calibration where they had actually tested this, and this allows me to show you a couple of different things here that you should pay attention to when you're looking at accelerometers, right? The one is a sensitivity, right? Also the excitation. These are strain gauge type devices, and so we'll talk more about strain gauges in another lab when we're looking at actually using them for force measurement. But strain gauges require some excitation, so this tells you you need to excite it with 5 volts. It needs power, right? And then you need signal conditioning off of that too. You may need an amplifier on the output. It probably uses it's a Wheatstone bridge configuration in this case. It gives you the sensitivity as 10 millivolts for every G, so it's really low response, and that says at DC. What does that mean? DC, think of it as like DC, like current. It's DC voltage. It's a constant value. So think of it with respect to here. This shows what you might know as a Bode plot or a frequency response plot, and this shows frequency on this axis, and this is sensitivity here. It's like the amplitude ratio. Think of this as having the value of the millivolts per G here. So what this says is that it's pretty flat here, and then at some frequencies, somewhere this is 50, that's 100 there, you can't see it, this is 200, at about 200 it starts rolling off, because remember, this is a mass spring damper system, so you can imagine the natural frequency is somewhere around here. It's an overdamped system. It's rolling off. It doesn't have this resonance. You don't want resonance in sensors. But this right here is what we call the bandwidth. This is the useful range over which you can use this sensor and have a constant sensitivity. That's the key. You don't want the sensitivity jumping around on you. You want it to be constant. You can then say that when I measure the output voltage, I can now convert that right into G's. And I can be assured that for all the frequencies of my signal, I can use the same constant sensitivity, and that's why it's so important to have this bandwidth that you can to have knowledge about. Also, this also says something about the range. I can use this accelerometer plus or minus 10 Gs, right, and so on, right. Just one last thing right here tells you the output leads from this accelerometer. I think I have a picture on the next slide. Yeah, it shows you how you make the connections. So it has 6 leads, and you actually connect, those 4 like to a Wheatstone bridge, right? So you can imagine the connections, and you have the input here, and then the output is here, the signal's here, and then this would probably go to an amplifier, right? Because you'd want a bigger signal. Okay. Take a look at these slides. I'll talk more about this in a related lab having to do with using strain gauges for force measurement. But you can see you can use them to also measure acceleration. A lot of the accelerometers that you might see today, the low-cost ones that you might buy from, say, SparkFun or from some of these other places, really low cost, anywhere from $4 up to $50, depending on what you're looking at, whether it's just an accelerometer or it's got a gyro, or it also has maybe a magnetometer on it. You might have an IMU. So a lot of these are MEMS devices. They're very small, and they're also, most of them are probably using capacitance type sensing. And what's happening is, imagine between the mass, and I'll show you some little pictures in a second, between the mass and the base, you have, like parallel plates. And as it accelerates in that axis, the distance between the plates is changing, and so that distance between the plates, this D, causes the capacitance to change. If you can now condition that, you put that capacitor or multiple capacitors in a bridge, in an impedance bridge, you can then be detecting that change in capacitance, which infers, right, which you can then infer acceleration from that, okay? And then you put that capacitance actually within a mechanical structure. Guess what? Yes, in the form of a mass spring damper. And then it has the appropriate dynamics that are predictable, right? It'll have a bandwidth and a reliable or a designed, right, range of frequencies over which you can make measurements, but then you can basically measure capacitance. The nice thing about capacitive sensors of this type is that built on structures, just like the piezoresistive one I just showed you, is that you can go to really low frequencies. In fact, you can go all the way down to DC, right? Remember that piezo sensor said you can go down to DC, which means 0 frequencies. In other words, constant acceleration. So you can actually pick up Earth's the gravity acceleration. In other words, you can pick up the fact that when you're not moving, you'll detect G, and you'll do that in the lab. So this also makes these kinds of accelerometers very small. I mean, you can make them very small, but it makes them very popular rather, to put in phones and to put in small devices and so on. So capacitive sensors are used in a lot of different ways. You can make level sensors, pressure sensors, even humidity sensors. In this case, of course, what might be changing is the permittivity. This shows the configuration with a beam for acceleration measurement and so on, right? And this shows another kind of how these found these figures from an old accelerometer that we used to use that you can probably still find, made by Analog Devices, a capacitive type accelerometer. Imagine the motion in this direction. This whole structure here, you can see when it starts moving, you have acceleration. The compliance of this structure gives you that stiffness, right? It's got some mass, some stiffness, and some implied damping in the system. And then look, what's changing is the distance between these little comb structures that are all micromechanical. And then you can just you have integrated electronics that can be used to detect that change in capacitance. You build an accelerometer. Okay. Just like the other accelerometers, these things are going to have some bandwidth, so you can see that you can go all the way down to really low frequencies before you start seeing this roll-off. That roll-off, right, is due to the mechanical resonance, right? Higher stuff might be there because of maybe other kind of structural effects, and even higher might be due to the signal conditioning. But the first roll-off that you see is always going to be to that first kind of K over M natural frequency due to the basic seismic device design that I talked about from the very beginning. Okay, one last slide. These sensors that also have gyros use a different kind of structure I won't talk too much about. I have, I think, a little reference here to a really early paper on when the first types of MEMS type gyros are being built. They might be built in different ways now, but a lot of these use kind of like almost like a fork, tuning fork type structure that when you rotate this guy, it excited a piezo structure that could then be picked up. You could pick up those vibrations. The motion of these tines down here was related to omega, And they talk about in this paper how that was used to design an angular rotation sensor for each of these axes. Imagine putting 3 of these, orthogonal to each other. Now you can measure the 3 axes of velocity rather. So this are also proportional measurements to velocity, right? Not acceleration.